Good morning. This is a course on Introduction to Probability Theory and Statistics. As I said earlier, we have first 8 modules or 8 topics on probability part, and the last 4 topics or modules are in statistics part. Already we covered one topic, that is descriptive statistics and sampling distributions, and the next topic is topic 10, that is estimation. In this topic we have already covered one lecture on point estimation. In the last lecture we have covered the introduction about the estimation, and then we have given the layman definition of estimator, then the definition of point estimator, and we have discussed a few examples on estimators. After that we have discussed few important properties of the point estimator. In this lecture we are going to discuss on how one can compute the point estimator. Even though there are many more methods, there are two important methods. One is method of moments and the other one is method of maximum likelihood. This we are going to discuss with one easy example. And the lecture 3 we are going to discuss about the interval estimation. So, let us move into the lecture 2, that is method of moments and method of maximum likelihood. Earlier we started with the estimator and we have seen the properties, but we did not discuss how one can find the estimator of unknown parameter of the population or unknown function of a parameter of the population. There are many ways we can find the estimator of the unknown parameters of the population. The first and very important method, that is called method of moments. That is by just simply equating the sample movements with their population counterparts and solve for the parameters we need to estimate. That is called the method of moments. That means as long as you have the assumption of distribution of the population, and that underlying distribution of the population having moments, if they are unknown, the parameters are unknown, obviously the moments are the functions of the unknown, moments are the functions of the parameters. So, whenever the parameters are unknown, you can estimate those parameters via equating the sample movements with the population movements. That is called the method of moments. For example, the population mean is mu, which is unknown. You can equate the sample mean with the population mean, then you can conclude the sample mean is going to be the estimator for the population mean directly. Similarly, one can go for make out if the population variance is unknown, sigma square, then you can conclude the sample variance is going to be the estimator for the population variance when sigma square is unknown. So, these are all the two easiest example of applying the method of moments logic to find out the estimator of the unknown parameters. This is the one parameter case. Like that you can think of many more concepts in this way. I am going to explain how one can easily able to do it for with this logic. We know that the random variable x is the random variable corresponding to the population distribution, and suppose you assume that the rth order moment exists, rth order moment about the origin exists, that you denoted by mu suffix r dash, that is expectation of x power r. X is a random variable which corresponding to the population distribution. Whenever the rth order moment exists, whenever the rth order moment exists for the population distribution, one can denote that is by mu suffix r dash, that is expectation of x power r, that is the rth order population moment about the origin, provided it exists. Fine. Now, you can same way you can make the notation for the rth order sample moments about the origin by m suffix r dash. We are using two different notation and you see it very carefully. The earlier one mu suffix r dash, that is the rth order population moment about the origin, whereas m suffix r dash, that is the rth order sample moments. Therefore, if you see it carefully, it is x suffix I. X i's are the random variable corresponding to the sample, random sample of ith one. Like that we have n samples. Fine. So, since the rth order population moment exists, obviously the sample rth order sample moment also exists. So, you can able to compute m suffix r dash using the samples. When I use the small letter, that means a small m r dash, that means I use the sample values to compute that quantity. When I write capital M suffix r dash, that means I am using a random variable of a random sample xi, therefore, it becomes a random variable. So, you got the notational difference. What the method of moment says, always the sample moments converges to the population moments, that convergence in probability. Therefore, you can conclude the rth order moment about the origin of a sample, that is going to be the estimator for the population moment of rth order about the origin. The reason is the convergence takes place in probability with the rth order moment of a sample moments converges to the rth order moment of population moments about the origin in probability. Therefore, you are equating, but this you are getting the estimator first as a function of we are getting the estimator for the moments. You know, the moments are the functions of parameters. For instance, suppose the population follows binomial distribution, which has the two parameters n and p. If both are unknown, then the population mean is np, that is mu. Population variance is np 1 minus p, that is going to be the variance sigma square. So, you can conclude first the sample mean x bar is the estimator for mu, which is NP, and similarly the sample variance S square is the estimator for the population variance sigma square, which is n into p into 1 minus p, correct. Once n and p are unknown, you solve both the equations, because there are two unknowns and you got two estimators. One is a sample mean x bar is the estimator, and the other one is a sample variance is the estimator, and you have np is equal to mu, and n into p into 1 minus p is the sigma square. So, you solve for it, then you get the estimator for mu and sigma square, because you have two estimators, two unknowns, you can solve and get the estimator for mu and sigma square. So, what I am giving an example is instead of one parameter is unknown, suppose you have more than one parameter is or parameters are unknown, then you can identify those many estimators, then solve for it. That is what it says in the previous page, that says we simply equate the sample movements with their population counterparts and solve for the parameters we need to estimate. Fine. Now, I am giving another example. Just now I have given the example for binomial distributed population. Now, you can think of the population follows a normal distribution with the parameters mu and sigma square, both are unknown. So, using the method of moments, you can find the estimators for mu and sigma square. So, whatever I said, you can make it as a nice form. You identify first sample movement, identify the sample variance, then you create a function, then solve for it, then you can get the estimators for mu and sigma square. So, that means you can create a nice function as the h of the first order sample movement, second order sample movement, and so on, rth order sample movement, then you can solve for it and get the unknown parameters, get the estimators for the unknown parameters. That is what we have done it here. So, therefore, you will get the estimator of population variance, which is unknown, that is going to be in terms of the sample movements, second order movement minus the first order movement whole square. If at all I made a mistake, you can correct it, because by hand written it is the draft is given. So, one can identify the estimator for the unknown parameters by identifying the sample movements or the estimator for the population movements, then solving you can get the answers. In this example, we are going to find the estimator of theta naught by using method of moments. So, the problem is like this: we have a random sample of size n from the population with the probability density function is given, that is a 2x times theta square, where x lies between 0 to 1 divided by theta, otherwise it is 0. This is a probability density function. So, the question is find the estimator of theta naught by using method of moments. Yeah, find the estimator of theta square by using the method of moments. So, find the mean and variance for the using the probability density function. By equating the population movements with the sample movements, we get the estimate of theta square. By doing simple calculation, you will get the estimate of theta square, that I denoted by theta square cap, that is going to be 1 divided by 2 divided by n summation y I is equal to 1 to n x I square. So, this is a estimator of theta square. As a remark, the method of moments is the oldest method of deriving point estimator. It almost always produces some asymptotically unbiased estimator, although they may not be the best estimators. The way I have explained in the last lecture, you can verify whether it satisfies unbiasedness, whether it satisfies the efficient or sufficient, consistent, all those properties we can verify. Because in the previous lecture we did not discuss how to compute the estimators. Now we are computing or finding out the estimator for the unknown parameters or function of unknown parameter. You can verify all those properties are satisfied or not. Sometimes a moment estimator does not exist also, because whatever the distribution of the population you assign, whether that distribution has the moment or whether it has the first order moment or second order moment or any nth order moment exists, then only it makes sense to use that concept to find out the estimator. So, therefore, since there is a restriction over the existence of moments of the population, therefore, for some you cannot find the estimator using method of moments. By the way, if you find the estimator using a method of moments, then we say it as a moment estimator. So, it is just name. Whenever you compute estimator using a method of moments, then we say it is a moment estimator. Similarly, we are going to discuss the another method in which we are going to find out the estimator, that is going to call a maximum likelihood estimator, because you are going to use the maximum likelihood principle. Fine. So, with this with the one method I am finishing here. Now, we will move into the second method. This is also very important method, that is called a method of maximum likelihood. So, this is one of the very important methods to find out the estimator of unknown parameter of the population. The principle what they say, that is called the maximum likelihood principle. That means in a layman, what is the joint probability density function in which the probability is going to be more. You identify the parameters in which maximizing the probability of occurrence, then those parameters are going to be called it as the maximum likelihood estimator. The parameters, the value of parameters in which the joint probability density function, which is going to give a more probability, that is going to give the estimator, that is called the maximum likelihood estimator. For that, first we create a function. This is called maximum likelihood function, that is nothing but the product of the joint probability density function of population in terms of samples. So, this word xi's are very important. That means you are having a probability density function of a population distribution, that is small f, and you are creating a likelihood function. You are creating a likelihood function as the product of joint, it is the product of probability density function of a population distribution in terms of xi's. Since each samples are the random sample, therefore, it is basically a joint probability density function, which is the product of probability density functions of each samples. Now, the thing is this is a function of theta, where theta is unknown. There is a possibility theta could be a vector also. There is a possibility that theta can be a vector also. So, in a simplest case, if the theta is a single variable, That means this likelihood function is the function with one variable theta. Now, the question is you have to find out what is the value of theta in which this function is going to be maximum. So, you go back to the calculus, you find out the first derivative with respect to theta, find out the second derivative with respect to theta, then equate first derivative to 0, identify theta in which the first derivative is going to be 0, then you substitute that value into the second derivative, check whether it is going to be maximum or minimum. Here you need a maximum, that means you have to make sure that condition is satisfied. Once you conclude the theta in which this function is going to be maximum, that theta is going to be the estimator of the unknown parameter theta. Let us see whatever I said. Let us have a simple example. The population follows a exponential distribution. We have taken n sample. Obviously, those random sample also follows the same distribution of the population, which is exponential distribution with the parameter lambda, and the lambda can take the value greater than 0. The question is find the maximum likelihood estimator for the unknown parameter lambda. Since we are going to use the maximum likelihood principle, this estimator is going to be called it as a maximum likelihood estimator. Fine. And in this case the population distribution has only one parameter. Therefore, you create a function that is a likelihood function L of theta, you can make it. There is a one more observation is whenever you have a likelihood function as the form of exponential of something, what you can do, you can make a logarithm of likelihood function, and instead of maximizing the likelihood function, you can go for maximizing, finding out the maximization problem on logarithm of likelihood function. Both are one and the same. Therefore, in the statistics most of the cases you will have a exponential family population distribution. There is a separate theory when we can conclude so and so population distribution is exponential theory, exponential family. So, this is also going to be exponential family population distribution. So, in that case you can go for logarithm of likelihood function, then you can apply the maximization over it. So, you find out how to compute. So, find out the derivative, total derivative with respect to lambda, then identify the lambda in which the function is going to be maximum. Since you have made it as a function of random samples, so you are getting 1 by lambda is going to be 1 by n times the summation of x size. So, that is nothing but the x bar. Therefore, at lambda is equal to 1 by x bar, this ln of likelihood function is going to be maximum. Therefore, the maximum likelihood estimator for lambda, that is lambda cap, it is a notation, that is going to be 1 divided by x bar. So, when I write capital letter, that means it is a random variable. When I write the small letter, that means it is a value. So, the lambda cap is a estimator, that is 1 divided by capital X bar. Fine. So, this is a way we are getting the estimator using the maximum likelihood principle. So, the same approach can be extended whenever you have more than one parameters are unknown for the population. So, when you have two parameters are unknown, things are going to be little complicated than the one parameter case. not only the partial derivative with respect to those unknown parameters, you have to use the concept of identifying parameters in which the function is going to be maximum. So, here the summarization of how one can get the maximum likelihood estimator. First you create the likelihood function, and whether you go for total derivative or partial derivative, whether it is a one variable or if it is more than one variables. If it is a one variable, you take the total derivative. If it is more than one variables, then you go for taking a partial derivative on the likelihood function. Again I am saying, if the likelihood function in the form of exponential, then you can go for logarithm of likelihood function also. Then equate to 0 and solve the simultaneous equations, you can get the maximum likelihood estimator for the unknown parameters. So, the only difference is, if it is a one parameter, then it is easy. If it is more parameters, then you have to apply the functions of several variable concepts based on how many parameters are unknown. Fine. Let us have one more example with the two parameters are unknown. Assume that the population follows a normal distribution with the mean mu and the variance sigma square, and both are unknown, and you are interested to find out maximum likelihood estimators for mu as well as sigma square. So, first you create the likelihood function, and since it is in the exponential form, you create the logarithm of a likelihood function. Then you go for finding the partial derivative with respect to mu and sigma square. It is very important, you are not partially differentiating with respect to sigma, you are partially differentiating with respect to sigma square. So, you should keep sigma square as the variable. Then you will get the equations accordingly. And solve for the likelihood equations by equating them to 0. Then you can able to get the estimator for mu cap, and not estimator for mu cap, the estimator of mu, that is mu cap, and the estimator for sigma square, that is a sigma square cap, that you can able to get it in terms of the random samples. So, if I write a small letter, that means it is a value, if I write a capital letter, that is a estimator. And you see the difference here, while doing the maximum likelihood estimator, you are getting the maximum likelihood estimator of sigma square, which is different from the sample variance in the form of a denominator is n instead of n minus 1. But however, for larger n, both the estimators will be approximately equal. That is another conclusion from two different estimators. That means, by using a method of moments, you are getting a sample variance is the estimator for population variance, whereas for the same problem you are getting 1 divided by n summation x I minus x bar whole square, that is as the maximum likelihood estimator, which is different from the sample variance, that is another estimator for the same population variance, which is unknown. Now, we are going to discuss one more example of finding the estimator of theta using maximum likelihood principle. Let us start the problem like this. Let y1, y2, yn are independent random variables, where y is our normal distributed random variable with the mean I times theta and the variance sigma square for I is equal to 1 to n. The question is, find the maximum likelihood estimator of theta on the basis of y1, y2, yn. Further, prove that this estimator is an unbiased as well as it is going to be a consistent estimator. So, there are three problems involved. First, we have to find out what is the maximum likelihood estimator for theta. Then you have to prove that is going to be unbiased estimator, and finally you have to prove that is also going to be a consistent estimator. So, you know the procedure how one can find the maximum likelihood estimator of parameter. So, here the parameter is theta. So, you first you create the likelihood function, then since it is in the form of exponential, so take a logarithm and then you apply the maximum likelihood principle. Instead of the original function, you apply over the logarithmic likelihood function. Then you do all the steps in the same way. Finally, you will get the estimator of theta, that is theta cap, using maximum likelihood principle. This principle we have already explained. So, I just use the procedure as it is. So, once we get the estimator of theta, that is the maximum likelihood estimator. Now, we will go for verifying whether this is going to be unbiased estimator. So, for that you find out the expectation of that estimator. If that is going to be same as the population parameter, then you can conclude that is a unbiased estimator. So, we are done with the unbiased estimator. Finally, you have to prove the estimator which you got it via maximum likelihood principle, that is also going to be the consistent estimator. So, this also we have already explained. It is sufficient to show the variance of theta cap tends to 0 as n tends to infinity. So, you find out the variance of theta cap, then you make a limit n tends to infinity, and your final answer is going to be 0 as n tends to infinity. Therefore, theta cap is the consistent estimator of theta. With this, let me complete the lecture 2 of topic 10, that is estimation. In this lecture, we have discussed only how to compute the estimator using two important methods. One is a method of moments and the second one is a maximum likelihood principle. These are all the not only methods to get the estimators, there are many more methods, but since it is an introductory course, we are stopping with the only these two methods of finding the estimators of the unknown parameter of the population. With this, let me stop the lecture 2. Thank you.